Alice and Bob are playing a game where they start out with two intervals. The first interval is from L1 to R1 and the second interval is from L2 to R2. In one move, either Alice or Bob can independently select any of these two configurations to play with, and suppose they select this configuration, then they are allowed to either stretch this interval as much to the right as they want, but they cannot go beyond this right border, which is x1, or they can extend the left border as much as they want, but they cannot go beyond the left border, which is 1. But if they don't want to play with this particular interval, they can also select this interval and try to increase it, extend it to the right by taking this R2 and placing it over here, or try to expand the interval by decreasing this L2 by taking it from here and then plugging it over here. So given L1, R1 and X1 and L2, R2 and X2, you have to figure out who will be the winner of this game. Now this is a very difficult problem to solve if you don't know how to solve it. So in this video, I will share some techniques using which you can solve any game theory problems that is impartial and that has perfect information. What do I mean by impartial? So impartial games are the ones where both the players have the same set of choice. There is no bias between whose move it is, whether it is Alice's move or Bob's move. Because no matter what the person is, they are allowed to select any of these configuration and then try to expand this interval to the left and to the right, and they are free to do anything that they want. So that is why this game is impartial, and this game has perfect information. That is, both the player already know about the rules of the game and all the configurations that can possibly arrive from this. So that is why any impartial and perfect game, any impartial and perfect game can be solved using the techniques that we discussed in this video. And in fact, this is one of the claims where you might think that okay, you might try to solve it and then it can be solved, but there is a theorem which says that any impartial and perfect game necessarily has to be solved by this theorem only. So that theorem is known as Sprague-Grundy theorem. But before we dive into that, let me quickly talk about the NIM game. So there is a game called the NIM game. If you're not aware of it, you can learn about it in this video. So in which you start out with certain pile. So there is a pile of stones over here. Let's say that the first pile contains x1 stone. The second pile contains x2 stones. Third pile contains x3 stones. And the fourth pile contains x4 stones. And the rules of the game are like before. Alice and Bob are playing a game, and in one round Alice can independently select any of the piles and then remove any number of stones from this pile, but that has to be greater than 0. So if she picks pile x3, so she has to do x3 minus some delta where delta is greater than 0. So you can even try to take the entire pile, so that is also allowed. You can also do x3 minus x3. This is the amount of remaining stones. So this is known as the famous NIM game, and even this problem is very hard to solve unless you know already how to solve it. So that is why I will not tell you how to solve this problem. Instead, I will directly tell you the answer to this problem, and then we will use this problem as a stepping stone to solve the problem that we discussed in the previous slide. So the answer to this game is Alice can win. So Alice loses if and only if the XOR sum, if and only if XOR of all xi's is 0. So basically, if x1 XOR x2 XOR x3 XOR x4, if it is 0, then whoever's turn it is to play, they will definitely lose the game. Now, how do you remember in future whether the person with 0 will win or the person with zor sum 0 will lose? Remembering it is very easy. Consider the empty pile. Empty pile has no moves that you can make. So the zor sum is 0. It means that whoever's turn it is to play, they will always lose. So that is why you can always remember one simple rule in the NIM games is that every pile you take the zor, and if the resulting zor is 0, then whoever's turn it is to move, they will lose. They don't have a winning strategy. I will not dive deep into the strategy that is involved because that is fairly standard. There are already a lot of resources out there on the internet for the NIM games. So now what I want to focus on is the Sprague-Grundy theorem, which says that let me write that down. Every impartial perfect info game is equivalent to NIM. Is equivalent to NIM game. It means that no matter what the problem is, but if it is coming from the game theory domain and if it is truly impartial and with perfect info, then the answer for sure will involve zor, and there will 100% be a way to convert that game into a NIM game. You just have to be creative about it. So, and then it also further says that it can be converted to a NIM game. And like suppose you have a lot of games that you are playing in this pile 1. So this is pile 1, and then this is pile 2, and then this is pile 3, etc. Then of course the XOR sum of all the piles will determine who the winner of the game is. Now let's go back to this problem again, and let's see if the theorem is actually true, and can this game be converted to a NIM sum game or not. So if this is indeed a NIM sum game, and this is just like your pigeonhole principle problems where you know that you have to identify which elements are the pigeons and which elements are the boxes. For example, in the pigeonhole principle, it says that if you have n boxes, but if you have n plus 1 pigeons, then there is at least one box that will contain more than one pigeon. And what is the application of it? The modulo. Like how do you know that something modulo n, like how do you know that two remainders would be equal? You realize that you only have n different slots, right? So then there has to be some two elements whose remainder will be equal. So this is one example of pigeonhole principle. So we have to be a little bit creative and figure out what are the NIM piles over here and how can we exactly convert this game to a NIM game, because solving this game is a bit tricky, but for NIM at least we know the answer, right? Which is the XOR sum of the piles. So you can see that in one move you are either selecting this configuration and this configuration. It means that you can treat this game as one pile of the NIM heap and this configuration as one pile of the heap that you use in the NIM game. But how it is actually a heap, because here you are not removing any stones, you are just extending the interval to the left and to the right. But if you think about it, how many choices do you have to extend the interval to the left or right? You can either increase it to r1 plus 1 or r1 plus 2 or r1 plus 3 or r1 plus 4 or r1 plus 5 up to r1 plus deltas, which reaches x1. So it means that how much gap do you have in this segment? You can see that that gap is like gap on the right hand side for the first configuration is nothing but x1 minus r1. And you can notice that whenever you do an operation, you have to reduce the gap at least by 1, but you can reduce the gap as much as you want. This means that in one operation, if you start with g of r1 stones, if you visualize this part as g of r1 stones, then in one operation you are allowed to take as many stones as you want from this pile, as long as it is greater than 1. Similarly, for this part, you are extending this element to the left hand side. It means that there are L1 minus 1. So if you see, g of L1 is equal to L1 minus 1. These are the gaps that are available. So this is, you can think of it as a nim pile with these many stones. Similarly, for this, that would become g of L2 is equal to L2 minus 1, and g of R2 would be equal to x2 minus R2. So you can see that this game is nothing but a nim game played on 4 different piles, and the number of stones in each pile is equal to this: x1 minus r1, l1 minus 1, l2 minus 1, x2 minus r2. So even if you don't know the answer to even if you don't know how to solve the nim game, and even if you don't care about it, at least you can see that if you can convince yourself that the answer to the nim game is really depending upon the XOR of all the elements, then you can also convince yourself that the answer to this problem will be simply the XOR of all of these elements. So that is it. That is the entire video. So in this, I just wanted to take one simple game, and I created this video because this problem appeared as problem E in a it was a it was a problem F. It was a problem F in a diff2 round, where this reduction of taking this interval and then converting it to a series of nim games with nim piles was the first step to that problem. And there was also a second step that deals with dynamic programming and number theory. So I will not discuss that in this video, but I hope you got some ideas about how to take any game and be creative and then convert it to a nim game, because that will always be possible 100%, because that is what this theorem says. You just have to figure out how to do that conversion so that you can identify what are the nim heaps corresponding to the new game.